I didn't think so. Could be wrong. There's a slight. Let's go.
It's going. Okay, folks, it's that time of the morning. I'm going to pass around the sign sheet. I am not certain what's going on with the screen, so I'm stuck with not using it this morning. What I am doing is I am going to make notes on my iPad, which is also logged into Zoom, so that if you miss anything, you'll have an opportunity to go back and get it. But due to whatever is going on with that screen, I cannot do things the way I would normally do them. So, first things first, announcements. I just wanted to remind everybody that you do have a quiz that is due at 11:59 p.m. It should have just now opened up. It is over material through Tuesday. So it's not over anything today. Number two, you do have a homework that is due Monday at 11:59 p.m. that is over today's material. Number three, I want to remind everybody with lab today, don't forget, even though it's hot outside and miserable, you do have to have on closed-toed shoes, pants, and goggles when you come to lab. Otherwise, you will not be allowed to enter the lab. Today's lab is not nearly as intense as last week's lab. And so I expect, though I could be wrong, that even by doing all of the laboratory and answering all of the questions, you will be done probably about an hour early, but that's a give or take. You know, I can't control how fast you move. If you and your partner are knowledgeable of the lab, it'll go much smoother than if you're trying to read the directions, which I will say that I noticed some folks did not do last week. So it is always important to read the directions. Now, today, the way things are going to work is, number one, I will open up only one door. You will walk in that door. We will be checking for closed-toed shoes, pants, and goggles. One lab partner should have a printout of the lab at minimum. That way notes can be taken because, and then when you get in, shortly after the start of class, there will be a quiz. The quiz will be over the background information only that is associated with the lab. So when you print off the lab, the first thing you see is the background, and it'll be over that information. And then because today's, because of the lab being, because we've already discussed everything associated with this lab, as soon as the quiz is done and I let you know, then everybody will be able to get started. Any questions about assignments or lab? I will expect this lab turned in today because it is easily doable in the time frame allowed. Okay, seeing no questions, then we are going to go ahead and get started. The first few days of this course has really been to provide you with tools that you are going to be using on and off throughout the semester. You know, with significant digits, if there's a mathematical calculation, you have to pay attention to significant digits for your homework, for quizzes, for lab. So it's a tool. You have to perform, you have to be prepared to use density, both to calculate density as well as to use density as a conversion factor. You have to be prepared to convert temperature all the way through the semester, because when we get to gas laws, we'll have to get it into Kelvin. You have to be able to do dimensional analysis, because that is what stoichiometry is a form of dimensional analysis. It's just dimensional analysis that is associated with chemistry. So all of the things we've really talked about are tools. They are not the chemistry. Today, we start the chemistry. And I am super excited because starting today, we are going to start on a journey, and the journey will begin today, and it will technically not end until the end of College Chemistry 2. But for College Chemistry 1, our journey, we are going to start by learning everything we can about the atoms of the elements. How many protons they have, how many neutrons they have, how many electrons they have, how to calculate the mass number, how to calculate the average atomic mass, how they are arranged on the periodic table, which is by far the best thing in the world, because if you know how things are arranged on the periodic table, you can guess a lot about that substance or about that element. That's going to take us a few weeks because we're also going to start looking at the quantum mechanics that went into understanding the arrangement of the electrons in an atom of an element, and ultimately getting into electron configurations, talking about the size of the atom based off of Z effective and stuff like that. So we're literally going to delve heavy into the atoms of the elements. Today is just going to be a quick brush stroke. Then we'll start combining those atoms of the elements in very specific ratios to make compounds. And we're going to talk about inorganic compounds that are ionic and inorganic compounds that are covalent. We'll get a little bit into the organic, but not very much at all. Once we talk about those, we're going to learn how to name them. And then we're going to move into understanding what they really look like by looking at Lewis structures, atomic shape, molecular polarity, and so on and so forth. After we know everything about the compounds, then finally we get into chemistry and start doing reactions, which is where most people want to go when they think about chemistry, is straight to the reactions. But you got to build it up. And we're going to talk about chemical reactions. You're going to learn to predict the products of some reactions. You are going to talk about the energy associated with a reaction. At that point, we're going to backtrack a little bit, and we're going to actually start talking about the individual types of substances in a little bit greater detail, which will lead you into college chemistry too. So lots and lots of information. But today it's all about the periodic table. And so I'm going to be spending some time over here. The very first thing you will note about the periodic table is that it is our elemental symbols. Folks, chemistry is a language, just like English, just like French, just like Spanish. Chemistry really is a language. The alphabet for a chemist are the elemental symbols. And there are correct ways always to write an elemental symbol. The first letter will always be capitalized, and the second letter will always be lowercase. They are always printed, not cursive. And when I talk about lowercase, I'm talking about the true lowercase, not an uppercase that's just written small. They have to look like this. And I will count off, and so will any other chemistry faculty member, will count off if you do not write the elemental symbols correctly. Now, these elemental symbols are unique to the element. And these elements have been named after people, properties, places, and planets. For example, argon up here, element number 18. Argon means inactive. Argon does not react with any other element. So that's an example where it's named after a property. Element 106 is named Seaborgium after Glenn Seaborg, who is very well known in the chemistry world. Element number 92, uranium, after a planet. And yes, there is plutonium up here, which I love, but you know, they got rid of Pluto supposedly as a planet. So, and then you have other places like Americium. Actually, starting at 95, 96, 97, 98, it tells you exactly where those elements were, all of them were found. 97 is berkelium. It was found at UC Berkeley. 98 is californium. UC Berkeley is in California. And 95 is americium because it's in America. So, you know, the symbols are unique to the name. Now, most of the symbols, they actually make sense with respect to the name. I gave you some examples. In other words, the symbols are related to the English spelling of the name. But some of the symbols especially the elements known to the ancients, have names that are related to Latin. Silver is after the element was originally named argentum, which is Latin. Gold, AU, was originally named aurum, which is Latin. Now, not all of them were Latin. We also have W, which is tungsten, which is wolfram. That was its original name, which is German, if I'm not mistaken. But the majority of the elemental symbols relate back to the element's name. There are some, and in the video that you were to watch, I gave you the list of the ones that were not. Now, the periodic table is not arranged haphazardly. The periodic table has predictive powers. But you got to understand how the periodic table is arranged. First of all, Mendeleev, he simply took all of the elements and he put them in order of their masses. Every once in a while, you'll find somebody that's out of order. But for the most part, they're in order of their masses. But then he took, and once he put them in order of their masses, he then arranged it so that all of the elements in the same column, called a group, behave similarly. So the neat thing about group number one, there's actually a fantastic video. Show it, but I can't. You can see how these elements behave. Group number one is known as the alkali metals. Which is ALKALI metals. That is true for everything but hydrogen. Now, the alkali metals, due to their electronic structure, if you throw them in water, you will get one alkali metal to one OH group. So we will make, if lithium's thrown in water, it makes LiOH. If sodium's thrown in water, it makes NaOH. I'm not crazy enough to throw francium in water, but guess what it's going to make? FROH. And I said I'm not crazy enough because as you go down a group, the reactivity increases. And to give you an example, let's just stick with this alkali metal, the alkali metals. If you throw lithium in water, it goes zzz, boring. If you throw sodium in water, you go zzz, and then at the very end, you get this little flame. If you throw potassium in water, it goes zzz, but it quickly looks like a sparkler. Rubidium will blow a hole in a bathtub. And I'm talking little bitty amount, like 2 grams. Cesium, 2 grams, will completely shatter a bathtub. So again, that reactivity drastically increased from hardly anything to a flame, to a sparkler, to blowing a hole, to completely shattering. Yes. Again, I don't know anybody that's crazy enough to do anything with francium. To be quite honest, I've never seen francium, whereas I have had a canister of cesium before. I never got to play with the cesium either. For the most part, I don't go past potassium because that's where I feel safe. I'll let other people that are a little bit crazier than me or who has the PPE, the protection, to actually do something with the crazier ones. Okay, so group 2 is known as the alkaline earth metals. ALKALINE earth metals. Folks, that's partially because if you look at any rock out there, you're going to probably find some calcium, some magnesium, and so they are found in the earth. Now, thinking of groups, since we've been talking about groups, group 17 is known as the halogens. HALOGENS. The halogens are your most reactive of the non-metals. And then finally, you have group 18, which is known as your noble gases. Because until you get to xenon, I think, I may be wrong. There may be one compound out there of krypton, but I think most of them, any compounds of the noble gases start at xenon. Because most of the top elements are unreactive and do not react with anybody. That's why they're called noble gases. They're also called noble gases because the elements are going to fight to have a electron configuration similar to those. So groups are your columns. Periods are your rows. Now, what is significant about the periods? The periods, when we get into the electron configuration, are going to give you an idea of where the electrons are located. Specifically, it's going to identify how far away from the nucleus the electron is. One reason that francium is so dangerous is because its electron is way out here compared to the nucleus. Francium doesn't even know its electron exists. So it's no big deal for it to be removed. Whereas if you're talking about hydrogen up here, the electron is right up against the nucleus. And so it's a lot harder to remove it. Not to say it isn't removed, because it is, but it's harder, energetically speaking. So the period is going to help you identify where the electron is, how far the electron is from the nucleus. Now, so that is one way by which we arrange our periodic table. The second way is by metals, metalloids, and nonmetals. Now, before I even get into it, I want you to memorize boron, which is element 5, silicon, element 14, germanium, element 32, arsenic, element 33, antimony, element 51, tellurium, element 52, and go ahead and go for polonium 84 and astatine 85. They form a nice little stair step. Basically, the way I memorize it, folks, is I take and I go, okay, boron, silicon, arsenic, tellurium, astatine. And then I go to the left and go polonium, antimony, germanium. Now, that's important because those are the metalloids. And the metalloids separate the nonmetals from the metals. The nonmetals are to the right of the metalloids on a periodic table. And the metals are to the left of the metalloids. Now, that particular division is important because metals form cations or positively charged ions. And if a non-metal forms an anion, if a non-metal forms an ion, it's going to be an anion, which is negatively charged. So knowing that division allows you to figure out what type of charge you would see on that particular element. The next division is going to be your main group elements, your transition metals, and your inner transition metals, better known as the lanthanides and actinides. Now, your main group elements are group 1, 2, 13 through 18 using the new numbering system. Now, I want to say on active, it may be the old numbering system. And so if it's on active, you may also see it written as A. 1, 2, and it would be 1A, 2A, 3A, 4A, 5A, 6A, 7A, 8A with the letter A. Whereas I prefer the new naming. I'm just saying that in case you see it on active. With the new one, the transition metals are groups 13 through, group 3 through 12. And with respect to the old system, they are labeled with B's, the letter B. folks, that particular division, that main group elements compared to transition elements, tell you something about the electron configuration of their ions. Group 1 and 2 will lose the correct number of electrons to make a noble gas configuration. The group over here is going to gain electrons to make the noble gas configuration. But transition metals, most of them cannot lose or gain enough electrons to get to a noble gas. So that becomes important when we start talking about that. There's also the inner transition metals called the lanthanides and actinides. Basically, you'll notice I actually like this periodic table, but the one you have that I just passed out to you is a little bit different. Oh, no, it's not. It's actually nice to you. You will notice you go from 56 down to 57. Basically, our periodic tables would be too long if we tried to write it out the way it should be written. These are called the inner transitions because they go in between the transition metals. But this row, this top row, is called the lanthanides because that is lanthanum. This bottom row is called the actinides because that is actinium. As we will discuss, chemists are not very creative with words. We basically say it as it is. Now, all of these things are part of your periodic table. And by the way, the periodic table I gave you today is going to be the one you receive on every single exam. You will get a fresh periodic table on every exam, and it will be this one. If you want, I can make you an extra copy for next time, and then you can make as many copies as you want so you can use it to write everything you need to write. Because we're going to get into that periodic table, and it's going to get crazy at times. Questions so far? Like I said, that periodic table is cool. It has predictive power. There was a long time where we didn't know what element 32 was. It took us forever to figure out what element 32 was. But they knew what element 14 and element 50 was at that point. They knew those two. And they're going, okay, because element 32 is in the same group as element 14 and element 50 is going to behave the same. So even though it didn't have a name for the longest time, I mean, it's been a long, long time since it hasn't had a name, but when they were discovering elements, because it didn't have a name, that was okay. They still knew how it was going to behave. They just had to find it. That's essentially what happened. One more thing I want to make note of on this periodic table that is on the wall is I want to make note of the color scheme. So if the element is in black, that means that it is a metal, a solid. Well, no, excuse me. The element is in black, it means that it is a solid. If the element is in red, it means that it is a gas at room temperature. If the element is in blue, it means that it is a liquid at room temperature. And as you will see, there's only two of those. And finally, all of the ones that are simply outlined means that those were man-made. At one of our national laboratories that has that capability. And trust me, it is wickedly cool what they can do. I got to see it in action one time, and it's wickedly cool. questions? Okay, let's take a 2-minute break if you don't mind. My voice is obviously cracking today. You can stand up and talk a little bit. Oh, thank you. Did everybody sign in? I had to say that. You want a periodic table?
Sorry.
They have come up to, let me put one, pick up one and put the rest back down.
I know, I was supposed to have somebody else's. Yeah, I have a lot of people.
Never wanted to.
Maybe it's just one of the days.
You don't have to go. It gets to walk on there, but.
You got this synthesize an element. Which one was that?
I actually don't know if the person just was saying, yeah, you know, they're working at some site. Try not to see the instrument and the people behind the computer that has that.
Where was it at?
It was out at Los Alamos. I got to play. Now I got to play the other stuff out in Los Alamos, right? I actually got to use high division there, and high school to do some movie. And now
Okay, let's get back to this, and hopefully we'll have time to play a game. But it all depends on what you do next. Can you answer the question? Okay, so hopefully, how many people watched the one about the different subatomic particles, atomic number, stuff like that? Protons, neutrons, electrons. Okay, well, let's just see what you remember then. How's that? Okay, so what? There are three subatomic particles: the proton, the neutron, and the electron. Who determines the identity of the element? Does that number ever change? No, because if you change the number, you change the identity. Is that number on the periodic table? Yes. What is it called on the periodic table? The atomic number. And where do I find that atomic number on the periodic table? It's the top number. I don't know where it is on, let's see. Yep, top right. Well, top left on the one I gave you. Top right on that one. Okay. So, what's the mass of a proton? Does anybody know that one roughly? 20.006767 AMUs. I'm not gonna make you memorize that number, but it's basically right at 1 AMU. Okay, so what subatomic particle is responsible for an element's reactivity? The electrons. Folks, that is the only number that is allowed to change, is the electron, when we start dealing with ions later on. So, an electron. In a neutral atom, how do we determine the number of electrons? It's equal to the number of protons, which is equal to the atomic number. Okay. The third subatomic particle, and it, by the way, has a mass of 0.0005 AMUs. In other words, it's really tiny compared to that of a proton. And in fact, they found the electron, and the electron didn't even come close to make it up for mass until they started finding the proton. And even with the discovery of the proton, it still didn't come close to find matching the mass of an atom until they found what? The neutron. A proton has a +1 charge, an electron has a -1 charge. What does a neutron have? It's completely neutral. What is the neutron responsible for? The isotope of the element. The neutron determines the isotope. Now, we have a number that is the number of protons plus the number of neutrons. What is it called? Mass number. Is the mass number found on the periodic table? If you say yes, raise your hand. If you say no, raise your hand. If you don't want to answer, raise your hand. It's okay. Folks, the mass number is, this is where I gotta break something you learned in high school typically. The mass number is not on the periodic table. What is on the periodic table is the average atomic mass, which we'll talk about on Tuesday. But the mass number is a whole number, and it is not found on the periodic table. So how are you supposed to know that? Well, you're not. I'll either have to tell you the mass number, or I'll have to give you the number of neutrons. One of the two. There's no way for you to know. For instance, chlorine has two different mass numbers. It's chlorine 35 and it is chlorine 37. Carbon actually has three. It's carbon 12, carbon 13, and carbon 14. Nitrogen has two, carbon 14 and carbon 15. I mean, nitrogen 14 and nitrogen 15. But you're not going to know that until you've got experience with them. So I'm either going to have to give you the mass number, or I'll have to give you the number of neutrons. So with that in mind, and yes, we've got about, 30 minutes. We're going to play Go Fish, where you make a book of two. What I have here, and you really don't need the periodic table, is a deck of cards. Now, this deck of cards, you will find, for instance, the word neon-20. What we're telling you with that is that it is neon, and the -20 is telling you the mass number. And you have to go, okay, so that 20 My mass number is 20. I look over and I see, oh wait, neon. So that means my protons equals 10. So that must mean it has 10 neutrons. So instead of saying, do you have neon 20? Because nobody's going to have it written as neon 20. You have to ask, do you have 10 protons, 10 neutrons? And if they do, you get a pair. Whoopsies, whoopsies, whoopsies. Oh well. You get a pair, and that's, and then the next, and just like with Go Fish, if you don't get it, you got to draw. Now we're going to use the rule where you only have to draw once instead of keep drawing. I know some people will keep drawing. If you call it, you get it, and it's, you get to keep calling until you don't get one. So we're going to have some fun in the last few minutes and work with the concept of mass number, protons, and neutrons. Okay, so divide up in groups of 4-ish. And one of the 4 come grab a deck of cards. And you get to have a little bit of fun in chemistry today. And you'll need your periodic table, and that's all you'll really need.